Okay. Let's analyze this thing. So the order of the nodes is clear. If you know what the Van der Waals data structure is, then you know why it's called this. Otherwise, see lecture 10 or so in the future. Forget exactly when we're covering it. So this order was not invented by Van der Waals, but it looks very similar to something else that was invented by Van der Waals, so we call it that. But that's the name of a guy, Peter. So analysis. Order is clear. The algorithm is clear. We follow our root to leaf path. What we claim is any root to leaf path and any value of b, the number of blocks visited is order log base b of n. So to do that, in the analysis, we get to know what b is. The algorithm didn't know. Algorithm here doesn't know b and doesn't need to know b. But to analyze it, to prove an order log base b of n bound, we need to know what b is. So while the algorithm recurses all the way down, keeps dividing these blocks into smaller and smaller pieces, we're going to look at a particular level of that recursion. I'm going to call that a level of detail. I'll call it straddling B. So my picture is going to be the following. These little triangles are going to be size less than B. But these big triangles are size greater than or equal to B. Okay, at some level of recursion, that happens. By monotonicity, I guess. I could keep going. I mean, this tree is going to have substantial height. I don't really know how tall it is, or that's sort of the central question. Drawing some pointers here. But just look at, if you subdivide all the big triangles till you get to these small triangles that are size less than b, then you stop recursing. Now the algorithm, of course, will recursively lay that out. But what we know, we recursively lay things out, and then we concatenate, meaning the recursive layouts remain consecutive. We never interleave two layouts. So however this thing is laid out, we don't really care, because at that point it's going to be stored in memory, which is this giant array. It's going to be stored in an interval of size less than b. So at worst, where are the block boundaries? Maybe draw that in red. Block boundaries are size b. We don't know exactly how they're interspersed, but let's say these are the block boundaries. So it could be that this little subarray falls into 2 blocks, but at most 2 blocks. So the little triangles of size less than b live in at most 2 memory blocks. So to visit each of these little triangles, we only spend 2 memory reads at most. So all that's left is to count how many of those little triangles do we need to visit. On a root to leaf path. I claim that's going to be log base b of n. So I guess the first question is, what is the height of one of these little triangles? Well, we start with a tree of height log n, then we divide it in half, and we divide it in half, and divide it in half, and we take floors and ceilings, whatever. But we repeatedly divide the height in half. And we stop whenever the number of nodes in there is less than b. So that means the height is going to be theta log b. In fact, it's going to be in the range half log b to log b. Probably with a paren that way. It doesn't really matter. Because you stop as soon as you hit b. You're dividing the height in half repeatedly. You might overshoot by at most a half. That's it. So height is log b. So if we look along a root to leaf path, each of these things we visit, we make a vertical progress log b, theta log b. And the total vertical progress we need to make is log n, and so it's log n divided by log b. So I guess 4 times log n, 2 log n over log b. Triangles, we reach a leaf. It's total progress we need to make, divided by half log b here, progress per triangle. So we get 2 times log base b of n. And then for each triangle, we have to pay 2 memory reads. So this implies at most 4 log base b of n memory transfers. And I implicitly assumed here that b is not 1, otherwise you need a b plus 1 here. But to be interesting. As long as b isn't 1, then it doesn't matter. Okay, so that's the log base b of n analysis. Actually really simple. Essentially what we're doing here is binary searching on b in a kind of weird way, using divide and conquer and recursion. So we say, well, maybe b is the whole thing. Then b equals n. Then we don't have to do anything. Everything fits in a block. Otherwise, let's imagine dividing here and supposing b is root n, and then we need 2 accesses. But b might be smaller than that, so we keep recursing, keep going down. And because we're dividing in half each time, we're not binary searching on b, we're binary searching on log b, which is the height of a tree with b nodes in it. And that's exactly what we can afford to do, and conveniently it's all we need to do, because to get log base b of n correct, you only need to get log b correct up to a constant factor. All right. Now, that was the easy part. Now the hard part is to make this dynamic. This is where things get exciting. This works fine for a static tree, and this is how we do search, but we can't do inserts and deletes in this world easily. But I'll show you how to do it nonetheless. So this is what's called a cache-oblivious B tree. We're going to do it in 5 steps. And the first step, unfortunately, is delayed till next lecture. So I need a black box. It's a very useful black box. It's actually one that we've briefly talked about before, I think in the time travel. If you remember, in time travel, there was one black box, which we still haven't seen, but we will do finally next lecture, which was you can insert into a linked list, and then given 2 items in the linked list, know which one comes before which other one in constant time per operation. Closely related to that is a slightly different problem called ordered file maintenance. Here's what it lets you do. You can store n elements, n words, in specified order, so just like it's a linked list. But we don't store it as a linked list. We want to store it in an array of linear size. So there's going to be some blank spots in this array. Got n items, an array of size, say 2n or 1.1 times n. Anything like that will suffice. The rest, we call them gaps, items, gaps in the array. And the updates, so this is physically what you have to do. You can change this set of elements by either deleting an element or inserting an element between two given elements. So this is just like the linked list updates. I can delete somebody from a linked list. I can insert a new item in between two given items in the linked list. But now it has to be stored in a physical array of linear size. Now, we can't do this in constant time. But what we can do is move elements around. Okay, so let me draw a picture. So maybe we have some elements here. They could be in sorted order, maybe not. There's some gaps in between. I didn't mention it, but all gaps will have constant size. So this will be constant size gaps. And we're able to do things like insert a new item right after 42. Let's say we insert 12. So 12, we could put it right here. No problem. Now maybe we say insert right after 42 the number 6. And we're like, oh, there's no room to put 6. So I've got to move some stuff. Maybe I move 12 over here, and then I put 6 here. And then I say, okay, now insert right after 42 the number 7. And I'm like, uh-oh. I could, move these guys over 1 and then put 7 here, and so on. Okay? Obvious algorithm to do this takes linear time, linear number of shifts in order to do one insertion. Claim is you can do an insertion in log squared amortized. It's pretty cool. So worst case, you're still going to need to shift everybody. But just leaving constant size gaps will be enough to reduce the amortized cost to log squared. And this is conjectured optimal, although no one knows how to prove that. And that's ordered file maintenance. Now, we're going to assume this is a black box. Next lecture, we'll actually do it. But I want to first show you how it lets us get cache oblivious dynamic B trees. Log base B of n, insert, delete, search. Okay. We're going to use an ordered file maintenance data structure to store our keys. Just stick them in there. Now, this is good. It's really not good for anything, although it's a starting point. It can do updates in log squared of n. No, I didn't mention this part. In a constant number of scans. So, think of these as this kind of shift. I have to scan left to right to copy 23 to the left, 42 to the left, and so on. Scans are things we know how to do fast in n over b memory transfers. So if you're going to do log squared, if you're going to update an interval of log squared guys using constant number of scans, this will take log squared n over b memory transfers. Not quite the bound we want. We want log base b of n. This could be larger or smaller than log base b of n. It depends how big b is. But don't worry about it for now. Okay, this is still, at least it's polylog. Updates are kind of vaguely decent. We'll improve them later. On the other hand, search is really bad here. I mean, we're maintaining the items, I didn't mention it, but we will actually maintain the items in sorted order. So yeah, you could do a binary search, but binary search is really bad cache obliviously, because most of the time you'll be visiting a new block until the very end. So binary search, it's a fun exercise, is log n minus log b. We want log n divided by log b. So we can't use binary search. We need to use Van de Boas layouts, this thing. So we just plug these together. We take this static search tree and stick it on top of an ordered file maintenance data structure. So here we have a Van de Boas layout static tree on top of this thing, which is an ordered file. And we have cross-linking. Really, here we have gaps. And we don't store the gaps up here. Do we? Yeah, sure we do, actually. Store them all. Put it all in there. All right, I have an actual example here. Let's do it. 3/7/9/16 21 42. Okay, cross links between, I won't draw all of them. Then we store all the data up here as well. And then the internal nodes here are going to store the max of the whole subtree. So here the max is 3, here the max is 9, 16, 42, 42, 42, and 9. Okay, if I store the max of every subtree, then at the root, if I want to decide should I go left or should I go right, I look at the max of the left subtree, and that will let me know whether I should go left or right. Okay, so now I can do binary search. I do a search up here. I want to do a search, I search for the tree. This thing is laid out just like this. And so we pay log base b of n to search up here. +1 if you want. And then, we get to a key and we're done. That's all we wanted to know. So search is now good. Updates, two problems. One is that updating just this bottom part is slow. Second problem is if I change the bottom thing, and now I have to change the top thing. But let's look at that part first. It's not so bad to update. I mean, this structure stays the same. Unless n doubles, then we rebuild the entire data structure. But basically, this thing will stay the same. It's just data is moving around in this array, and we have to update which values are stored in this structure. The layout of the structure, the order of the nodes, that all stays fixed. It's just the numbers that are being written in here that change. That's the cool idea. So that's step 2. Let's go to step 3. Actually, kind of wanted that exact picture. It's okay. I need to specify how updates are done. So let's say I want to do an insertion. If I want to insert a new key, I search for the key. Maybe it fits between 7 and 9. Then I do the insertion in the bottom structure, in the ordered file. So maybe we want to insert 8. These guys move around. Then I have to propagate that information up here. And the key thing I want to specify is an update does a search. Then it updates the ordered file. That's going to take log squared n over b. And then we want to propagate changes into the tree in post-order traversal. That's the one thing I wanted to specify, is it actually matters in what order I update the items. So for example, suppose I move 9 to the right and then I insert 8 here. Okay, so then this thing, let's do it. What changes in that situation? Well, 9 will change to an 8 here, which means this value has to change to an 8, and this value needs to change to an 8. And this one I can't quite update yet because I need to do the other tree. So here I change this value to 9. This one doesn't change, so this is OK, this is OK, this is OK. Just taking the maxes as I propagate up. So the red things are the nodes that I touch and compute the maxes of, and the order I did it was a post-order traversal. I need to do a post-order traversal in order to compute maxes. I need to know what the max of this subtree is and this subtree before I can recompute the max of the root. Okay? So it's really the obvious algorithm. Now the interesting part is the analysis. So searches we've already analyzed. We don't need to do anything there. That's log base B of n. But updates are the interesting thing to analyze. And again, we're going to look at the level of detail that straddles B, just like before. So let me draw a bit of the picture. I'm going to draw it slightly differently from how I drew it last time. Okay. What I'm drawing here is actually the bottom of the tree. So a real tree is like this. And I'm looking at the bottom where the leaves are because I care about where I connect to this ordered file. So there's the ordered file at the bottom. I'm refining each triangle recursively until their size less than b. They're going to be somewhere between root b and b. These big triangles are bigger than b. Okay. So that's where I want to look at things. Now, when we update in the ordered file, we have this theorem. It says you move elements in an interval. So what changes is an interval. The interval has size log squared n amortized. So we're updating some interval here, maybe something like this. And so all of these items change. Let's say. Now this is not going to be too big. It's going to be log squared n amortized. And all of the ancestors of those nodes have to be updated, potentially. So, all these guys are going to get updated. Some of this tree, this path, all of this stuff is going to get updated. Some of this stuff, a path up to here. The path up to the root gets updated in general. And all these nodes get touched. Now I claim that's cheap. No more expensive than updating down here. Let's prove that. Okay, first issue is, in what order do I visit the nodes here? I want to think about this post order. Okay, maybe I'll use another color. Draw that. So let's say we start by updating this guy. We update this value. Then we go, I'm doing a post order traversal, this tree. And once I've completely finished here, I can go up here, maybe go up here, visit over down this way, visit, fix all the maxes here. Then I go up, fix all the maxes here, up, fix all the maxes. So the maxes, when I come up, then I can fix the maxes up here, and so on. Okay, think about that order. If you just look at the big picture, which is which triangles are we visiting, what we do is we visit this triangle, then this one, then this triangle, then this one, then this triangle, then this one. Or I guess this is the better picture. This triangle, left one, this triangle, next child, this parent, next child, this parent, next child. And when we're done, we go over to the next big triangle. Within a big triangle, we alternate between two small triangles. As long as we have 4 blocks of cache, this will be good. Because there's at most 2 blocks for this little triangle, at most 2 blocks for this little triangle. So jumping back and forth between these is basically free. So we assume, white chalk. We assume that we have at least 4 blocks of cache. Post-order traversal alternates between 2 little triangles. So this part is free. The only issue is how many little triangles do I need to load overall? Sorry, I should say I'm just looking at the little triangles in the bottom 2 levels. So this is in the bottom 2 levels. Sorry, I forgot to mention that. As soon as you go outside the bottom big triangle, let's not think about it yet. We'll worry about that later. So just looking at these bottom 2 levels that I drew, we're just doing this alternation. And so the only issue is how many little triangles do I have to load? So there could be these guys. These guys are good because I'm touching all these nodes, and the number of nodes here was bigger than b. So if I take this divided by b and the ceiling doesn't hurt me because the overall size is bigger than b. These guys have to be a little bit careful. Here the ceiling might hurt me because I only read some of these nodes. It may be much less than b. It could be as low as root b. I divide by b, take the ceiling, I get 1. So I have to pay 1 at the beginning, 1 at the end, but in between, I get to divide by b. So the number of little triangles in the bottom 2 levels that I visit is going to be 1 plus log squared n over b amortized. The size of the interval is log squared n amortized. So this would be if I'm perfect, but I get a plus 1 because of various ceilings. Okay, and also the number of blocks is the same. Because each of these little triangles fits inside at most 2 blocks. So it's going to be order 1 plus log squared n over b. Okay, so I can touch all those in this much time. Because I assume that I can alternate between 2 of them quickly. And once I finish one of these leaf blocks, I never touch it again. Okay, so I visit each block essentially only once, as long as my cache is this big. Cool. So that deals with the bottom 2 levels. I claim the bottom 2 levels will only pay this. And we were already paying that to update the ordered file, so it's no worse. Now, there's the levels above this one that we can't see. I claim that's also okay. Sorry. Also need number of memory transfers. Is equal to that. Okay, one more part of the argument. levels above the bottom two. Nice thing about the levels above the bottom two is there aren't too many triangles. All right, well, there aren't too many nodes involved. Let's see. So down here, there were like log squared n nodes. That was a lot of nodes. Once I go up 2 levels, how many of these nodes can there be? These roots. Well, there's log squared n at the bottom, and then I basically shaved off a factor of b here. So the number of these roots is at most log squared n over b. That's small. For those nodes, I could afford to do an entire memory transfer for every single node. Okay, so the number of nodes that need updating, those are ancestors, is order log squared n over b. That's the number of leaves down there. At some point, you reach the common ancestor of those leaves. That tree, so here, draw a big picture. Here's the bottom 2 layers. Okay, we're shaving that off. Up here, the number of nodes here, these roots that we're dealing with, that's the log squared n over b. So if we build a tree on those nodes, total number of nodes in here is only log squared n over b times 2, because it's a binary tree. But then there's also these nodes up here. This is potentially log n nodes. So the number of nodes that need updating is at most this plus log n. Okay. So what's going on here is we first analyzed the bottom 2 layers. That was okay because of this ordering thing, that we're only dealing with 2 triangles at once, and therefore we pay this size divided by b, which is log squared n over b. Then there's the common ancestors of those nodes. That forms a little binary tree of size log squared n over b. For these nodes, this triangle up here, we can afford to pay 1 memory transfer for every node. So we don't care that we're efficient up here. Which is, I mean, well, let's not worry about whether we are. It doesn't matter. So for these nodes, we pay at most 1 memory transfer each. And so we pay at most log squared n over b for them. That's fine, because we're already paid that much. And finally, we have to pay for these nodes up here, which are from the common ancestors of these guys, up to the root. And that has length at most log n, could be smaller if this was a big interval. So for these guys, we pay order log base b of n. Why? Because this is a root to node path. And this is the static analysis. We already know that following a root to node path, we pay at most log base b of n. Okay, so we pay log base b of n plus log squared n over b for this, plus log squared n over b for this, plus log squared n over b for the ordered file. So overall running time for an update is log base b of n plus log squared n over b. We actually paid log base b of n twice, once to do the initial search. I said an update first has to search for the key, then it updates the ordered file. That's where we pay the first log squared n over b. And then to propagate all the changes up the tree, we pay log squared n over b for this part, and then another log base b of n for this part. Whew. Okay, that's updates with a bad bound. But turns out we're almost there. So at this point, we have searches optimal, because searches are just searching through the Venn and DeBose thing. That's log base b of n. Updates, not quite optimal. I mean, for not quite matching a B tree, I should say. This is not an optimal bound we're aiming for. We're just aiming for B trees. We'd want to get this bound, same as searching. But we have this extra term, which if b is small, for example, if b is log n, this term will be bigger than this one. The breakpoint is when b equals log n times log n. Okay, so for small b, we're not happy, and we want to be happy for all b simultaneously. So I want to fix this. We're going to fix it using a general technique, great technique, called indirection. So this is step 5, indirection. Idea is simple. We want to use the previous data structure on n over log n items. And well, we need to store n items. So where do we put them? On the bottom. So I'm going to have theta log n nodes down here, theta log n nodes next to them, or items, I should say, theta log n. Okay, and then one of these items, let's say the min item, gets stored in this tree. And the min item over here gets stored in this tree. The min item here gets stored up here. Okay, so this item only, the data structure we just developed, I only store n over log n of the items. The rest that fit in between those items are stored down here. Now I use standard B-tree tricks, actually. If I want to do an insertion, okay, how do I do a search? I follow a root to leaf path, and then I do a linear scan of this entire structure. How much does it cost to do a linear scan of log n? Only log n divided by b. This is smaller than log base b of n, so the hard part of search is the log base b of n. Okay, how do I do an update? Well, first I search for the guy, I find the block that it fits into, and just insert into that block. Done. As long as this block doesn't get too big, I can do, how do I insert into a block? Rewrite the entire block. It's a scan, it only takes log n over b. So it's basically free to rewrite this entire block every time as long as it has size at most log n. If it gets too full, then I split it into two parts that are half full. Okay, so in general, each of these blocks will maintain the size to be between 1/4 log n and log n. So if it gets bigger than log n, I split it into two guys of half size. If it gets smaller than 1/4 log n, then I'll merge it with one of its neighbors and then possibly have to resplit it. Or you could think of it as stealing neighbors from your siblings. That's what you do in B trees. But with a constant number of merges and splits, you can restore the property that these guys have sizes very close to half log n. And so if they end up getting full, that means you inserted half log n items. If they ended up getting empty, that means you deleted 1/4 log n items. And so in both cases, you have log n items to charge to. Whenever you do an update up here, so we update up here every time we split or merge down here, because this guy has to keep track of the blocks, not the items in the blocks. So we effectively slow down the updates in the top structure by a factor log n. Which is great, because we take this update bound and we get to divide it by log n, which removes this square. So we end up with, so we used to have log base b of n plus log squared n over b. We get to divide that by log n. Plus we have to do this part at the bottom. Okay, plus we're doing log n over b at the bottom. So basically this log cancels with this square. So this is log n over b as well. This thing gets even smaller. So we end up being able to do updates in log n over b. Not really, though, because at the beginning we have to do a search to figure out where to do the update. If you knew where you had to update, you could update a little faster. You could update in log n divided by b. If you don't know where to update, you've got to spend log base b of n to search initially. Okay, but that's the fun part. We can now update this data structure fast just with this one layer of indirection with log n chunks at the bottom, speeding this data structure up by a factor of log n for updates. Searches don't take any longer. Just pay this extra term, which was already much smaller than what we were paying before. Whew. That's cache oblivious B trees, other than ordered file maintenance, which we'll do next class.